as we pick up on example 4 here, it asks us to now consider the function g of x equals the integral from 3 to x of f of t dt. Keep in mind that f of t is still that same graph from up above. Okay, so it is still the same graph from problem 3. Okay. Now, the difference is that on this last one, this was a 0, right? This was supposed to be k. This was a 0. You have it changed in your notes, I'm sure. This time the difference is 3 to x. Thoughts on where is the 0 of g? If g is defined to be the integral from 3 to x.
Like the top of the curve?
Not necessarily the top. No, not the top of the curve.
Where it starts. So at 3.
Huh?
At x equals 3.
It's going to be at x equals 3.
So
Now, why did you say that?
because that's where the integral starts.
Okay. It's where the integral starts. If you put in 3 for x, you're going to have the integral from 3 to 3. And what's been happening when you have the integral from a number to itself? It equals 0, right? Because you can't do the area from 3 to 3. It just doesn't exist. So, yeah, the key is there. Since right there, that's where it's starting. You're looking at that. Then they ask us the question, what is g of 0? It does exist.
But it's not in the integral.
So, okay, so if we think this through, g of 0 means what? We're doing the integral from 3 to 0 of f of t dt, yes? Now, the weird part about this is integrals are designed to go from smaller number to larger number. So this integral really needs to go 0 to 3 instead of 3 to 0, which comes up, I think it's in the next lesson we talk about properties of integrals and we learn a property there. But if you look, let me go back here, from 0 to 3, okay, I know they say 3 to 0, but if you look at 0 to 3, what would that answer have been? What do we know at 3?
4.
It was 4.5, right? So now the key is that when x is 0 on this one, it's not going to be exactly 4.5 though, because here's the deal. This, we said, we already answered on the first question, where is the 0 of g? So the 0 of g is going to be at 3, right? Keep in mind, what's that doing? That's taking this graph and moving it down 4.5. Okay? All of this is going to move down. Where's that going to put this area of 4.5 at? It's going to put it below the x-axis. If area is below the x-axis, what's it become? Negative. Okay? So the integral rule we'll learn next, I think it's next lesson, is in order to get this integral properly, it's the integral from 0 to 3, but I forgot to put the negative out front. It's the opposite, so negative integral from 0 to 3 of f of t dt. Okay, so when we ask what is g of 0, it's the opposite of the integral from 0 to 3. Well, if you look up there from 0 to 3, it was 4.5. But the opposite of that is going to be negative 4.5. Okay? Is that making some sense? It's one that it is a harder one for me to explain sometimes. I do admit that. So, as I said, the key here is we already said the 0 is at 3, right? Well, basically what's happening now is basically all these values Is that how I even want to draw that in there? I guess it's how I drew it in my notes, but all these values are shifting. So this at 3, it was up at 4.5. Well, now it's at 0. Okay, all these values are going to be shifting, and that will kind of come into play here. Did we talk about it? It'll come into play here in a couple more questions. So let's go through the rest of our questions. Domain of G. Is our domain going to change? No, we still have the same inputs, right? We still have the inputs of what to what? 0 to 10. So that's still the inputs of 0 less than or equal to x less than or equal to 10. Total change in G. Is that going to change? It's still based on this same graph, yes? Okay. It's still based on the same original f of t graph. So is the amount of change what is it? Total change? As remember, total change was the difference from the ending to the beginning. Even though this is shifted down, in other words, like right here, that was shifted down.
So it doesn't matter that there's
Mm-mm.
So then that would
It's still gonna end up being the same amounts. Okay, so there's still, even though my beginning and ending amounts are going to be different, they're still going to have a difference of 6 between each other, if that makes sense. Okay, so that total change is still going to be 6. So if you look, the total change on E up above, we did, I don't know if I wrote anything in, but we looked at the end it was 6, at the beginning it was 0. We're still going to have that. Now, max value of G.
take 12
Mhm.
minus 45.
Mhm. Yeah.
Is 7.5.
Yes. I feel like that was the big question right there. Is that, yeah, you're going to take, it was 12 on the previous problem, right? But now we've got to lower it by 4.5, and 12 minus 4.5 is 7.5. If we can do our basic math today, right? Where will it occur?
Equals 6.
Same place the previous max occurred, right? The last max occurred at 6. This one will occur at 6. Now, range. What was my range on the last one?
Negative 12, negative 4, 5, 2, 7.
Mm-hmm. Yep. So now we're going negative 4.5 less than or equal to y less than or equal to 7.5. And then they ask us to sketch this graph of G in green. Well, if you go back up here, what's happening? My max of 12 became to be at 7.5, right? This value at 3 that was at 4.5 is now at 0. Each of these values is moving down 4.5 units. Okay, so what was at 0, 0 is now going to be at negative 4.5. Okay, what was at 1 comma 1/2 is going to be at 1 comma negative 4. What was at 2, 2 to negative 2.5, right? Call me out if I make a mistake here. At 3, 4.5 is at 3, 0. what was it, 4, 8. So 4 comma 3.5. 5, 11. 5, 6.5. 6, 12, I've already done. It's now at 6, 7.5. You don't have to worry about 7 if you don't want. If we want to jump to 8, 9. It's now at 8 comma 4.5. And if we skip 9 and go to 10, 6, it's now going to be at 10 comma 1.5. When I connect these, what do you notice? The shape is the same. Okay. Now I believe, yeah, I almost forgot there for a moment. Top of the next page, we have a few follow-up questions. Still on the same problem. So top of the next page, they ask us to describe the relationship between all f of x, where it's the integral from k to x of f of t dt, as k takes on different values. So in example 3, k was 0. In example 4 here, k is 3. What's it doing?
It just shifts.
It what?
The graph shifts.
It shifts, yes. And specifically is a vertical shift. Okay. So it's just going to be all f of x in this case are going to be vertical shifts of each other. Okay. So all capital F of x are vertical shifts of each other. Okay. What point must lie on the graph of any given family member and why?
Zero.
Okay. What would that ordered pair be?
For this specific.
Well, okay, so go for the specific one, yes.
3, 0.
Okay, so that was 3, 0. And where did that 3 come from? It was my what value?
No, not
The range
K.
that.
It was your
Yeah, okay.
k value, yes? Okay, so you're starting to catch on to what I'm looking for. 3, right here, was our k, right? And when we put in 3, it became a 0, yes? Okay. Yep, your k value will create a 0, and I don't have it up on the top portion, but on number 3, it was, the 0 was at 0, but my k value was 0. So what point must lie on the graph? K comma 0, okay? And then it says y, and I basically, when the lower bound equals k, the area from k to k, the integral k to k is going to equal 0, is what I have written here. So lower bound equals k, the area from the integral k to k of f of t dt equals 0. K. Let's see if we can do some fill in the blank. Part K. As K takes on different values, the functions f of x equals the integral from k to x of f of t dt graph as blank transformations as one another. What kind of transformations would you say there? Vertical. Okay. Has vertical transformations of one another, each containing the particular point k comma 0 we already talked about. Even though the lower bound changed is f prime of x equal f of t. Okay, I feel like there should be a comma or something in there. That doesn't read right all of a sudden when I read it out loud. In my head, it read fine earlier. Right there out loud, didn't read fine. Even though the lower bound changed, is capital F prime of x equal to f of t. And so, basically, if you look at this right here, I like to use this. If you take the derivative of f prime, that's capital F prime, right? What's going to happen when you take the derivative of an integral? And I know we're just learning this, but a derivative and an integral, well, an integral is what we call an antiderivative. A derivative and an antiderivative are going to undo each other. And so if you take the derivative of this integral, what's going to be left? The f of t. Okay, so the question, is that equal to that? Yes. Okay. And I think that, I feel like they're kind of jumping ahead. I feel like that comes up a little bit more in the next lesson, maybe. And my lessons are kind of blur of what's what in this, what's in which lesson, but. Okay. Questions on 4? Shall we try 5? Okay. On 5, shown below is the graph of the derivative f of some function capital F. Assume capital F of negative 3 equals negative 8. So traditionally, you can see the curve here, yes, and you can see the areas under the curve are already marked. We can't find the areas because these aren't curves we can find, but they're providing us the areas under each of the curves, okay? Traditionally, what do? When we start at the left, we just start from the left and we start accumulating as we move ourselves across to the right. The difference here is they give us what we call a starting value, that f of negative 3 equals 8. And so what we know, negative 3 is right here, yes. So we know at negative 3, our starting value is that f of negative 3 equals negative 8. At that point, that is what the value is equal to. Now, with that in mind, as we look at A, they ask us to find f of 2. Which means, what do we normally do to find f of 2? You take the areas and you add them up, right? Or add or subtract, depending on the scenario. Okay, what you're looking at is right here. What is our starting value? Negative 8 at this point. So what are we going to start with? We're going to start with negative 8. We're going to then what? Add 10. Then what? Add 26. And realize that 26 is not just left of the y-axis there. That 26 goes from what? Negative 1 to 2. On the screen it shows us red, and I know it's all one shading, but to me I almost feel like, oh, we're missing something, but no, that 26 is that whole area there. We're going to f of 2, right? So we're accumulating up to 2. So what is negative 8 plus 10 plus 26? That is 28. Okay? So as we move to the right, we were accumulating or adding our values, yes? Okay, what about f of 6? Can we basically start at what we already had?
Yeah.
And then what are we doing?
Subtract 8.
Okay. I'm writing it as add negative 8 because I'd already put add without thinking of it. And then add 14, right? Remember that 8 is below the x-axis, so it is assessed a negative value. 28 minus 8 plus 14 is going to be 34, I think. Is that right?
Yeah. Yes.
Okay. What about f of negative 5?
Zero.
No?
80.
I don't think it's 0, is it? No.
18.
You'd subtract negative 8 minus 18.
Okay. So we still have at negative 3 this starting value of negative 8. It is our starting value on all of these problems. What's the difference here?
Go backwards.
You're going backwards, you're going left. So what are we going to do? We're going to subtract. So even though this 18 is above the x-axis, we are subtracting the 18. And negative 8 minus 18 is negative 26. Okay. Okay, so I saw that I just had it written in my notes. This is what you often hear referred to as the initial value. Okay? You aren't always given an initial value, but when you are, you have to use it. Otherwise, you would assume you just start from the left and accumulate to the right. Or I guess you don't assume. They usually give you that beginning value at the bottom of the interval. Okay, so D, moving on here. Since the area under F is positive on the interval from negative 3 to negative 1, we know that the graph of capital F must be blank on the interval from negative 3 to negative 1.
X-axis.
So F is positive here, yes? And what is it? Shown below is the graph of the derivative of F of some function
Oh, it's
capital F. Okay, so since the area under F is positive, what about the graph of capital F? Think in terms of when the derivative is positive, what's the original graph doing? Increasing. Okay, that's the connection that we are looking for. Okay. Now, look at the vocabulary again. Since the area under F accumulates at an increasing rate, we know that the graph of F must be blank on this interval negative 3 to 1. When there's an increasing rate. No.
oh, speeding up.
No. I'm trying to think of a... Sorry, my brain is not there on how to lead. I'm lost on the lead. Think in terms... Sorry, my brain has to catch up. What do I want to say? Okay, so we're going back to first semester, obviously, and my words are not there right now. My apologies. When f was positive, so when we had a positive derivative, it makes the original graph increase. Okay? When we talk about the area under f accumulates at an increasing rate, we're still talking increasing, but we throw in that increasing rate, we start talking about concavity. When we start talking about increasing or decreasing, we talk about the rates, we're talking about concavity. So an increasing rate is going to make the graph be what? Concave up. We had a chart back, in that first book that tied it all together.
I thought it could be
Increasing rate is the key word here. Okay, it could be. It's the fact, it's not just because it's increasing, it's an increasing rate is the key. Because an increasing rate is going to mean a positive second derivative that's going to mean the concave up. Okay. Now, the area under f from -1 to 2 accumulates at a blank rate, so f must be blank on the interval -1 to 2. So from -3 to -1, we had an increasing rate. Okay? From what's happening from -1 to 2? It accumulates at a decreasing rate. And we talk about decreasing rate, we are talking about concave down. Now, we're going to use this information about increasing, decreasing, concave up, concave down to help us sketch our graph. Because on G, they ask us to sketch a graph of f showing extrema, inflection points, and horizontal tangents. Okay? Now, let's go through and fill in some points here. So we have our points. We already know several of these. F of -5, didn't we already fill that out? F of -5 from part C was -26. Do we know f of -3? I'll come back to that one. F of -1? No. F of 2? 28. F of 4? No. F of 6? 34.
Would f of -3 be?
It would be. Yeah, I was like, okay, I'm going to grab the ones we know. And f of -3, that was our given, yes. I totally spaced on that one. That was our given. We knew that right off the bat, didn't we? Sorry. F of -1. We didn't have to find that one up here, but where are we going to be at? -8 plus 10 is going to be 2. F of 4. What's the closest thing we knew? We knew f of 2 to be 28, right? So if f of 2 is 28, f of 4 is 20 when you subtract that 8. Okay, so let's put the points on. We are sketching the graph of capital F of x. I'm going to put my points on. -5, -26, -3, -8, -1, 2, 2, 28, 4, 20, and 6, 34. Okay. If we go back right here and use our information about -3 to -1, for instance. I don't even feel like I used that. I don't really like my looks of my graph that much here. Okay. But -3 to -1. We talked about that the area under the graph is positive, and so this graph is increasing, which obviously from -3 to -1, those points are going to be increasing, right? The area is accumulating at an increasing rate, so concave up just means, and there's not, it's kind of hard to do here. Yeah, it's kind of hard to do here because of the way the points are. But that technically is supposed to be concave up. I'm trying to figure out how I'm going to make that happen there. I'll be honest, on mine it just kind of looks like a line connecting the points. That's why I'm trying to figure out exactly how I'm supposed to make that happen. From -1 to 2, it was accumulated at a decreasing rate, so it was going to be concave down. So, let's see if I can make this. I don't know if I can make this happen. So what did we say? We said concave up, concave down. That's kind of a concave up to concave down-ish, right? Okay. So, from 2 to 4, it's below, so there's your decreasing there. And I don't think, yeah. Oh, it's hard because of the way these points are to get them exactly right, but and I don't have anything labeled. I mean, the extrema kind of show up along the way. The inflection points kind of show along the way. So, and I know they said to label or show horizontal tangents, but I don't see any horizontal tangents, so I'm not sure why that one. And I don't think she had any horizontal tangents labeled in hers either, so I didn't exactly understand that one. So, okay, guys. One more page. Okay. On this back page, I'm talking about some justifications here. In differential calculus, we use the derivative f prime to discuss properties of a function f. Thus, going back to if the derivative is positive, increasing graph, those type of things. In integral calculus, we need to reverse our thinking. Our new goal is to use derivative functions to talk about antiderivatives. In the example below, that we say that g, okay, right here, g is an antiderivative of f, because g is the integral of f. Antiderivative is what an integral is. So let's summarize the relationships between the properties of a function and its antiderivative. So you will notice here that this graph that you're showing here is the picture of f. Okay. Now, with this in mind, the connection I like to go with is when you take the derivative of g, so g prime, if you take the derivative of g, what's that going to mean in terms of f? What happens when you do the derivative of an integral? Or in other words, a derivative of an antiderivative? They essentially, loosely said, they undo each other. So g prime, if I take the derivative of g, it's going to be g prime. The derivative of this antiderivative is just going to be f, okay? Which, yeah, you can say f of t, the idea here is this graph is f, yes? That means this graph is also g prime, if you will. Okay? So, debate, do I want to label or do I want to figure it out as we go? I'll label as I go, I guess. F is positive on the interval from 0 to 8. Agreed? It's positive on the interval from 0 to 8 because it is above the x-axis. So G is blank on this interval. Okay. Normally, sorry, I'm really struggling with how I want to explain this today. Give me a moment here to I'll use that. Because we're reversing our thinking. I'm slow to reverse my thinking, obviously, today. I thought I looked at this morning. I obviously didn't look at it well enough because my brain is not straightened out enough. So F is positive here, right? F is also the derivative of G. There we go. That's what I needed to think of. So when I say that F is positive, what else am I saying? G prime is positive. Fair enough? That's the connection my brain needed to make. If G prime is positive, so if the derivative of G is positive, what's that say about G on that interval? It's increasing. Now, this right here over to the left, we had a chart like this in first semester, right? Okay. Don't necessarily pair it with these F's and these G's, but just the idea that if the derivative is positive, it means the original graph is increasing. If the derivative is negative, it means the original graph is decreasing, right? Okay. So when I say F, every time we say F, we're also talking about G prime. So if the derivative is positive, then G is increasing. Yes, no?
Yeah.
Can I make that connection okay?
Yeah.
Okay. F changes sign at blank. No.
X equals 0.
0 to 8.
Yeah. And I'm only using 8 because here's the deal. Where does this problem starting us at? Officially, it's starting us at 0. So I know I had to look, I was like, wait, am I using both? I don't remember. We're only using 8 there. F changes signs at 8, yes? So G must have a relative blank since F goes from blank to blank. So what's F go from? Okay. F goes from positive to negative. So what's that mean? A max, right? Because positive means increasing to negative means decreasing. So there is a relative maximum there. Okay? And so right here, this it would be, well, I guess I'll see if I'm going to put those in later. Okay. The graph of G is decreasing where F is negative. For values of when X is what? What values of X is what we're looking for here?
Bigger than 8. Bigger than 8 is 0. Or just forget about that.
Forget about 0. And I'm going with, she didn't use answers of anything below 0 here because this integral is listed as starting at 0. So, I mean, unless I'm forgetting something and it's going to matter someplace else, basically, I'm ignoring that piece just because we're starting at 0 here. Okay? The graph of F is increasing on, where is F increasing? 0 to 4. So G is well, we're not, F is concave down right here, but that's not what it's asking. Okay, we're asking about G. And it's the fact that F is, what was the word we used? Accumulating at an increasing rate. Is that what it said on the other page? It's back to that same idea there, increasing rate. So it is concave up. Okay. The graph of G is concave down where F is for values
4 greater than or equal to X, 4 or less. I don't know the signs. 8. 4 and 8.
and actually past 8
4 less.
Infinity.
because, yeah, mine just says X greater than 4. I mean, if you're going to use interval notation, I don't know. Yeah, mine just uses the X greater than 4. So the graph of G is concave down where F is decreasing for values X greater than 4. The graph of F has a maximum at
4.
X equals 4. So G has an
0.
Point of
inflection point. Okay. I say we've answered everything. I say because on my picture, and I don't know if I've done this in the past first, but yeah, everything that I have labeled on my picture is stuff that we have answered in the paragraph there. So my connection with these, and you saw it took me a little while to get my brain going in the right direction. I'll try and get better as I get better into this semester, is to connect with, okay, what are they asking, you know, when they're talking about F, okay, how does F relate to G, and backtrack from there, okay? On the bottom, There's another one of these charts. When the derivative f is blank, the antiderivative is such. So derivative f, and this is g, noticing that g is the antiderivative here. When your derivative function f is positive, the antiderivative, or in other words g, is going to be increasing. Negative obviously is decreasing. When your derivative function is increasing, then we're talking concave up. Decreasing obviously concave down. When we talk about the derivative function f changing sign, so crossing the x-axis, then we are talking about an extrema. Okay. Or another fancy word for extrema, extremum point.
Okay, I was gonna say I didn't think there was
The word that you've been taught and is most familiar to you
right.
is extrema. And we don't even necessarily say extrema point, it's just extrema. This is another fancy word. Realize you see that? Fancy for extrema. Okay? Okay. Hopefully, I'll be better off next time we do this, but work to get these connections, folks. I'll work to get my connections better because my connections were not there today. Okay, you have, was it 2 pages front and back, basically? Yeah.
4 questions.
4 questions with anywhere from 5 or 6 parts, either. So,